Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
Édouard Lucas, a name perhaps less immediately recognizable than some of his contemporaries in the mathematical world, nevertheless left an indelible mark on number theory. His exploration of integer sequences, primality testing, and recreational mathematics yielded results that continue to resonate within both pure mathematical research and applied fields like cryptography. Lucas possessed a remarkable ability to bridge abstract theoretical concepts with concrete, engaging problems, a characteristic evident throughout his diverse body of work. Central to Lucas's legacy is his profound investigation of what are now known as Lucas sequences. This work, deeply intertwined with the earlier contributions of Leonardo Pisarno, more famously known as Fibonacci, sought to generalize the properties observed in the Fibonacci numbers and to develop new tools for analyzing the nature of prime numbers. Fibonacci, in his Liber Abbaci of 1 1832, introduced the sequence where each term is the sum of the two preceding ones, starting with 0 and 1. This sequence, 0, 1, 1, 2, 3, 5, 8, 13, and so on, appears in surprising places throughout mathematics and the natural world. Lucas, recognizing the inherent mathematical beauty and potential of this sequence, embarked on a journey to unlock its deeper secrets and to extend its applicability. The problem Lucas addressed was fundamentally one of generalization. He questioned whether the specific starting values of 0 and 1 were essential to the unique properties of the Fibonacci sequence, or whether other similar sequences, defined by the same recurrence relation, might exhibit equally interesting or even more revealing characteristics. He also sought to harness the properties of these sequences for the practical task of determining whether a given number is prime, a problem of enduring importance in number theory. Lucas's method involved defining a family of sequences, now bearing his name, using a second-order linear recurrence relation. These sequences, denoted as u sub n of p, q and v sub n of p, q, are defined by the following relationships: u sub 0 of p, q equals 0, u sub 1 of p, q equals 1, and u sub n of p, q equals p times u sub n minus 1 of p, q minus q times u sub n minus 2 of p, q for n greater than or equal to 2. Similarly, v sub 0 of p, q equals 2, v sub 1 of p, q equals p, and v sub n of p, q equals p times v sub n minus 1 of p, q minus q times v sub n minus 2 of p, q for n greater than or equal to 2. Here, p and q are integer parameters that determine the specific characteristics of the sequence. The Fibonacci sequence itself is a special case of the Lucas U sequence, where p equals 1 and q equals -1. This connection provided Lucas with a powerful framework for exploring the properties of the Fibonacci numbers within a broader context. By varying the values of p and q, Lucas could generate a multitude of related sequences, each with its own unique set of properties. For instance, the Lucas sequence, often referred to as the companion sequence to the Fibonacci sequence, is obtained when p equals 1 and q equals -1 in the v sequence. This yields the sequence 2, 1, 3, 4, 7, 11, 18, 29, and so on. The terms of this sequence, while closely related to the Fibonacci numbers, exhibit distinct characteristics that proved valuable in Lucas's investigations. Lucas also explored the connection between these sequences and continued fractions. He demonstrated that the ratios of consecutive terms in certain Lucas sequences converge to quadratic irrationals, providing a link between number theory and the theory of approximation. These connections further solidify the importance of Lucas sequences as a tool for exploring the intricate relationships between different areas of mathematics. One of the initial and most significant applications of Lucas sequences was in the development of primality tests, particularly for Mersenne numbers. Mersenne numbers, aimed after the French Marin Mersenne, are numbers of the form 2 to the power p minus 1, where p is a prime number. Mersenne primes, which are Mersenne numbers that are also prime, have long fascinated mathematicians due to their relative scarcity and the computational challenges involved in determining their primality. Lucas recognized that the properties of Lucas sequences could be leveraged to create efficient primality tests for Mersenne numbers. His initial approach, while refined later by himself and others, laid the foundation for the Lucas-Lehmer primality test, a cornerstone of modern prime number research. This test, which we will explore in greater detail later, provides a deterministic method for proving the primality of Mersenne numbers, ever exceeding the efficiency of trial division, especially for large numbers. Fibonacci's Liber Abbaci served as a direct wellspring of inspiration for Lucas. The seemingly simple sequence that Fibonacci introduced sparked Lucas's curiosity and prompted him to seek generalizations and applications that Fibonacci himself may not have envisioned. Lucas's work built directly upon Fibonacci's foundation, extending the reach and impact of the Fibonacci numbers into new and exciting areas of number theory. The enduring historical significance of Lucas sequences lies in their role as a foundational element in number theory. They provided a powerful framework for exploring the properties of integer sequences, for developing primality tests, and for uncovering connections between different areas of mathematics. Lucas's work has influenced generations of mathematicians, inspiring further research into the properties of these sequences and their applications in diverse fields. Even today, Lucas numbers retain relevance. For instance, the Bailey-PSW primality test, a probabilistic primality test widely used in computer algebra systems, incorporates Lucas sequences to improve its accuracy. This test, while not deterministic in the same way as the Lucas-Lehmer test for Mersenne numbers, provides a highly reliable method for determining the primality of general integers. The inclusion of Lucas sequences in this test underscores their enduring value as a tool for prime number detection. The Bailey-PSW test's effectiveness stems from its combination of a Miller-Rabin primality test with a Lucas sequence-based test, providing a robust check against composite numbers masquerading as primes. Lucas's legacy extends beyond the specific results he obtained. His work exemplifies the power of generalization in mathematics, the importance of seeking connections between seemingly disparate areas, and the enduring value of exploring the properties of integer sequences. His contributions continue to inspire mathematicians and computer scientists alike, ensuring that his name will forever be associated with the fascinating world of prime numbers and their intricate properties. The pursuit of prime numbers, those elusive integers divisible only by 1 and themselves, has captivated mathematicians for millennia. Among the many facets of this pursuit, the efficient identification of large primes presents a particularly compelling challenge. Édouard Lucas made a monumental contribution to this area with his development of a highly effective primality test specifically tailored for Mersenne numbers. Mersenne numbers take the form 2 to the power of p minus 1, where p itself is a prime number. These numbers, named after the Frenchman Mersenne, hold a special place in prime number theory. Mersenne, in the 17th century, conjectured which primes p less than or equal to 257 would yield a prime Mersenne number. While Mersenne's conjectures contained some inaccuracies, his work stimulated considerable interest in these numbers and their primality. The problem Lucas directly addressed was devising a method to determine whether a given Mersenne number, 2 to the power of p minus 1, is prime, without resorting to the computationally expensive method of trial division. Trial division, which involves testing divisibility by all primes up to the square root of the number in question, becomes impractical for large Mersenne numbers. Lucas devised an elegant and efficient algorithm, now known as the Lucas-Lehmer primality test, specifically designed for Mersenne numbers. This test relies on a recurrence relation to determine primality. Test begins with a sequence S sub I, defined by the following rule: S sub I is equal to S sub I minus 1 squared minus 2. The initial value of the sequence, S sub 0, is set to 4. The Lucas-Lehmer test states that the Mersenne number 2 to the power of p minus 1 is prime if and only if S sub p minus 2 is congruent to 0 modulo 2 to the power of p minus 1. In simpler terms, we iterate the recurrence relation p minus 2 times, and if the resulting value of S sub p minus 2 is divisible by the Mersenne number, then the Mersenne number is prime. To illustrate the Lucas-Lehmer test, consider the Mersenne number m sub 7, which is equal to 2 to the power of 7 minus 1, resulting in 127. We begin with S sub 0 equal to 4. Then S sub 1 is equal to 4 squared minus 2, which equals 14. Next, S sub 2 is equal to 14 squared minus 2, resulting in 1094. Continuing, S sub 3 is equal to 94 squared minus 2, which equals 3786 to 34. Then S sub 4 is equal to 86 to 34 squared minus 2, resulting in 1 billion to 316,337,354. Next, S sub 5 is equal to 1 billion to 316,337,354 squared minus 2, resulting in a very large number. Instead of calculating the explicit value, we can take this number modulo 127, 1,416,337,954 squared minus 2, modulo 127 is equal to 12. Finally, S sub 6 is equal to 12 squared minus 2, which equals 12 leaves 10.42. Taking this modulo 37, we find that 12 leaves 10.42 modulo 37 is 0, since S sub 5, which is S sub p minus 2, is congruent to 0 modulo 127. The Lucas-Lehmer test confirms that 127 is prime. The computational advantage of the Lucas-Lehmer test over trial division is significant, especially for large Mersenne numbers. Trial division requires checking divisibility by all primes up to the square root of the Mersenne number. The Lucas-Lehmer test, on the other hand, involves a fixed number of iterations of a relatively simple recurrence relation. Each iteration involves squaring and subtracting 2, followed by modulo operation. These operations can be performed efficiently by computers, making the Lucas-Lehmer test a highly practical method for testing the primality of large Mersenne numbers. Mersenne's original conjectures concerning which primes p would yield prime Mersenne numbers directly influenced Lucas's work. Mersenne's assertions, though partially inaccurate, provided a specific set of numbers for mathematicians to investigate. Lucas, driven by the challenge of verifying or refuting Mersenne's claims, sought a more efficient method than trial division. His successful development of the Lucas-Lehmer test provided precisely the tool needed to advance this investigation. The impact of Lucas's work on subsequent discoveries of large prime numbers is undeniable. The Lucas-Lehmer test became the cornerstone of the search for the largest known prime numbers. With the advent of computers, mathematicians were able to apply the Lucas-Lehmer test to increasingly large Mersenne numbers, leading to the discovery of many new primes. A particularly notable example is the Great Internet Mersenne Prime Search, or GIMPS, a collaborative project that utilizes distributed computing to search for Mersenne primes. GIMPS relies heavily on the Lucas-Lehmer test, running the algorithm on numerous computers simultaneously to explore a vast range of Mersenne numbers. This project has been instrumental in discovering many of the largest known prime numbers, demonstrating the enduring power and practicality of Lucas's test. Derek Henry Lehmer, whose work refined and extended Lucas's original test, stands as a direct beneficiary of Lucas's foundational contribution. Lehmer's improvements to the algorithm further enhanced its efficiency and applicability, solidifying its place as the premier method for Mersenne prime detection. Without Lucas's initial breakthrough, the subsequent advancements and discoveries in this area would have been significantly hampered. Lucas's exploration of prime numbers, particularly Mersenne primes, served as a springboard into another fascinating area of number theory, Diophantine equations. These equations, named after the ancient Greek mathematician Diophantus of Alexandria, involve finding integer solutions to polynomial equations. Lucas directed his attention towards specific types of Diophantine equations, especially those intertwined with Fibonacci and Lucas numbers. The challenge inherent in Diophantine equations lies in the restriction to integer solutions. While polynomial equations over real or complex numbers may have infinitely many solutions, the requirement that the solutions be integers drastically limits the possibilities, often rendering the problem far more difficult. Lucas investigated equations where the unknowns were constrained to be integers, seeking to determine whether solutions existed and, if so, to find all of them. A central theme in Lucas's work was proving that certain Fibonacci or Lucas numbers are perfect powers. A perfect power is an integer that can be expressed as an integer raised to an integer power greater than 1, such as a perfect square or a perfect cube. Lucas tackled the problem of identifying which Fibonacci numbers could also be perfect squares, cubes, or higher powers. For example, he contributed to the proof that the only square Fibonacci numbers are 1, which occurs twice, as the first and second Fibonacci numbers, and 144, the 12th Fibonacci number. This may seem like a simple assertion, yet its proof demands sophisticated techniques. Lucas employed a combination of algebraic manipulation, modular arithmetic, and the inherent properties of recurrence relations to establish such results. His methods often involve analyzing Fibonacci and Lucas numbers modulo various integers. By examining the remainders, when these numbers are divided by specific moduli, Lucas could derive constraints on possible solutions to Diophantine equations. This modular arithmetic approach allowed him to eliminate vast swaths of potential solutions, narrowing down the search to a manageable set. Furthermore, Lucas skillfully exploited the recurrence relations that define Fibonacci and Lucas numbers. The fact that each term is the sum of the two preceding terms provides a powerful tool for relating different Fibonacci numbers to each other. Lucas used these relationships to construct identities and congruences that aided in solving Diophantine equations. Consider the problem of finding solutions to equations of the form x squared minus d times y squared equals n, where d and n are integers. This type of equation, related to the pill equation, arises frequently in number theory and has deep connections to quadratic fields. Lucas developed techniques for analyzing these equations, drawing inspiration from the work of earlier mathematicians such as Fermat and Euler. Fermat's contributions to number theory, particularly his work on finding integer solutions to equations and his method of infinite descent, demonstrably influenced Lucas's approach. Fermat's challenge to find all integer solutions to x squared plus 2 equals y cubed spurred significant mathematical advancement. Euler, in turn, built upon Fermat's ideas, developing methods for solving various Diophantine equations and exploring the properties of quadratic forms. Lucas, inheriting this rich legacy, refined and extended these techniques to tackle problems involving Fibonacci and Lucas numbers. Lucas's work provided a foundation for addressing more complex Diophantine problems. The techniques he pioneered, such as modular arithmetic and the exploitation of recurrence relations, continue to be valuable tools in number theory. His contributions paved the way for later mathematicians who sought to solve even more challenging Diophantine equations. A particularly noteworthy example of Lucas's influence can be seen in the work of Alan Baker on linear forms in logarithms. Baker's theorem, a powerful result in transcendental number theory, has been used to solve a wide range of Diophantine equations, including those involving Fibonacci and Lucas numbers. While Baker's methods are far more advanced than those available to Lucas, the underlying spirit of searching for integer solutions and exploiting the properties of numbers remains the same. Baker's work provided effective bounds on the sizes of solutions to certain Diophantine equations, allowing mathematicians to determine all solutions in a finite amount of time. The problem of determining all perfect power Fibonacci numbers, a question to which Lucas contributed significantly, was eventually resolved completely through the application of Baker's theorem and related techniques. This complete solution highlights the enduring legacy of Lucas's initial investigations and the subsequent advancements that built upon his foundations. Lucas's techniques, while not directly providing the ultimate solution to every Diophantine problem he considered, laid crucial groundwork. His focus on modular arithmetic, recurrence relations, and the creative manipulation of algebraic identities provided essential tools and insights that subsequent mathematicians expanded upon. The spirit of his approach, characterized by a relentless pursuit of integer solutions and a deep understanding of number properties, continues to inspire research in Diophantine equations. Furthermore, Lucas's work underscores the interconnectedness of different areas within number theory. His exploration of Fibonacci and Lucas numbers led him naturally to Diophantine equations, revealing the deep connections between recurrence sequences and the search for integer solutions to polynomial equations. This interconnectedness remains a hallmark of modern number theory, where ideas and techniques from diverse areas are often brought together to solve seemingly intractable problems. The impact of Lucas's work extends beyond the specific Diophantine equations he solved. His contributions helped to shape the landscape of number theory, inspiring future generations of mathematicians to pursue the challenging and rewarding quest for integer solutions. His influence can be seen in the development of new techniques and the application of existing methods to a wider range of problems. The legacy of Édouard Lucas endures as a testament to the power of ingenuity and perseverance in the face of mathematical challenges. The quest for integer solutions to polynomial equations and the exploration of recurrent sequences, so central to Lucas's number theoretic investigations, found an intriguing parallel in his contributions to recreational mathematics. Here, abstract mathematical principles acquired tangible form, accessible even to those without formal training. Lucas possessed a remarkable ability to bridge the gap between advanced mathematical concepts and engaging puzzles, fostering a wider appreciation for the beauty and power of mathematical thinking. His most enduring creation in this realm is undoubtedly the Tower of Hanoi puzzle. The Tower of Hanoi, initially marketed as Professor Klaus's Tower of Hanoi, an anagram of Professor Lucas, presents a deceptively simple challenge. The puzzle consists of 3 pegs and a set of discs of different sizes, which can slide onto any peg. The discs are initially stacked on one peg in order of decreasing size, forming a conical tower. The objective is to move the entire stack to another peg. Obeying the following rules, only one disc can be moved at a time, and a larger disc may never be placed on top of a smaller disc. Lucas provided a complete analysis of the puzzle, demonstrating a recursive solution that elegantly captures the problem's inherent structure. The recursive approach involves breaking down the problem into smaller, self-similar subproblems. To move the largest disc, the nth disc, from the source peg to the destination peg, one must first move the top n-1 discs from the source peg to the auxiliary peg, then move the largest disc to the destination peg, and finally move the n-1 discs from the auxiliary peg to the destination peg. This recursive process continues until the problem is reduced to moving a single disc, which can be done directly. This recursive solution yields a precise formula for the minimum number of moves required to solve the puzzle with n discs. The formula is 2 to the power of n-1. For example, with 3 discs, the minimum number of moves is 2 to the power of 3 minus 1, which equals 7. With 4 discs, the minimum number of moves is 2 to the power of 4 minus 1, which equals 15. The exponential growth of the number of moves with increasing end highlights the computational complexity inherent in even seemingly simple problems. The Tower of Hanoi puzzle also reveals a fascinating connection to binary numbers and break codes. A break code is a sequence of binary numbers in which only one bit changes between successive numbers. The sequence of moves in the Tower of Hanoi puzzle can be mapped directly to a break code, where each move corresponds to a change in one bit of the binary representation of the disk positions. This connection underscores the underlying mathematical structure of the puzzle and its relationship to fundamental concepts in computer science. The Tower of Hanoi elegantly addresses the problem of demonstrating recursion and mathematical induction in a tangible and accessible manner. Recursion, a powerful technique in computer science and mathematics, involves defining a function or procedure in terms of itself. Mathematical induction is a method of proving statements that hold for all natural numbers by first proving the statement for a base case, usually n equals 1, and then showing that if the statement holds for n, it also holds for n plus 1. The Tower of Hanoi provides a concrete example of both these concepts, making them easier to understand and appreciate. Consider the case of solving the Tower of Hanoi with 3 disks. Initially, the disks are stacked on the source peg. First, move the smallest disk to the destination peg. Then, move the middle disk to the auxiliary peg. Next, move the smallest disk from the destination peg to the auxiliary peg. Now, move the largest disk to the destination peg. Following this, move the smallest disk to the source peg. Then, move the middle disk to the destination peg. Finally, move the smallest disk from the source peg to the destination peg. This sequence of 7 moves completes the puzzle. For 4 disks, the process becomes more intricate, requiring 15 moves. The recursive nature of the solution becomes even more apparent as the number of disks increases. Each move is carefully orchestrated to ensure that the rules of the puzzle are followed and that the overall goal of moving the entire stack to the destination peg is achieved. While the precise influences on Lucas in the creation of the Tower of Hanoi remain somewhat shrouded in mystery, it is plausible that he drew inspiration from earlier mathematical puzzles and games involving rearranging objects according to specific rules. However, Lucas's unique contribution lies in his formalization of the puzzle, his analysis of its recursive structure, and his derivation of a formula for the minimum number of moves. His clever marketing of the puzzle under the pseudonym Professor Klaus further contributed to its widespread popularity. The Tower of Hanoi has had a lasting impact as a teaching tool in computer science and mathematics, influencing subsequent generations of problem solvers. It is a staple example in introductory programming courses, illustrating the power and elegance of recursion. It also serves as a valuable tool for teaching mathematical induction and for exploring the relationship between mathematics and computation. Its modern relevance persists in teaching recursion and algorithm design. Students learn to decompose complex problems into smaller, manageable subproblems, a skill that is essential for developing efficient and effective algorithms. The Tower of Hanoi remains a captivating and insightful puzzle, demonstrating the beauty and power of mathematical thinking in a tangible and accessible way. The puzzle provides a hands-on way to understand the concept of exponential growth, a phenomenon that appears in various fields, from computer science to finance. It encourages critical thinking and problem-solving skills, fostering a deeper appreciation for the elegance and efficiency of recursive algorithms. The simplicity of the puzzle belies its profound mathematical depth, making it a valuable tool for educators and learners alike. His recreational mathematics, exemplified by the Tower of Hanoi, provided an accessible entry point to mathematical thinking, complementing his more advanced work in number theory. Beyond his work on the Fibonacci sequence and the Tower of Hanoi, Édouard Lucas made significant contributions to several other areas of mathematics, including binomial coefficients, figure-8 numbers, and the theory of distributions. His investigations into these diverse topics reveal a consistent ability to connect abstract mathematical concepts with concrete, accessible examples. Lucas's work with binomial coefficients explored their properties and relationships to other mathematical structures. He delved into the arithmetic properties of these coefficients, examining their divisibility and congruence relations. Binomial coefficients, represented as n choose k, or the number of ways to select k items from a set of n items without regard to order, appear in various mathematical contexts, from combinatorics to probability theory. Lucas provided elegant proofs and insightful observations regarding their behavior. For instance, Lucas's theorem, a cornerstone in number theory, offers a method for computing binomial coefficients modulo a prime number. Specifically, it states that if p is a prime number, and then n k are non-negative integers, then n choose k is congruent to the product of n sub I choose k sub I modulo p, where n sub I and k sub I are the digits in the base p representation of n and k, respectively. This theorem simplifies the computation of binomial coefficients in modular arithmetic, a task that arises frequently in cryptography and computer science. Ernst Kummer's earlier work on ideal numbers and congruences provided a foundation for Lucas's investigations into the divisibility properties of binomial coefficients. The application of Lucas's theorem extends to areas such as coding theory, where modular arithmetic is used to construct error-correcting codes. Figure-8 numbers, also known as polygonal numbers, held a fascination for Lucas. These numbers, which can be represented by geometric arrangements of points forming regular polygons, connect arithmetic with geometry. Triangular numbers 1, 3, 6, 10 square numbers 1, 4, 9, 16 and pentagonal numbers 1, 5, 12, 22 are examples of figure-8 numbers. Lucas explored the relationships between different types of figure-8 numbers, deriving formulas and identities that illuminated their interconnectedness. He investigated their properties, such as their generating functions and recurrence relations. Specifically, Lucas examined the sums of figure-8 numbers and their connections to binomial coefficients. For example, the sum of the first n triangular numbers is equal to n plus 2 choose 3, a direct link between figure-8 numbers and combinatorics. Diophantus's work on arithmetic provided some inspiration for Lucas's investigations into integer solutions and number patterns, which later connected to figure-8 numbers. Figure-8 numbers find applications in various areas, including art, architecture, and computer graphics. The arrangement of objects in a triangular or square pattern can be aesthetically pleasing and structurally sound. In computer graphics, figure-8 numbers can be used to generate geometric shapes and patterns. Lucas also contributed to the theory of distributions, an area of mathematics closely related to probability theory. His work focused on the study of probability distributions and their properties, including their moments and characteristic functions. Lucas explored the concept of mathematical expectation, a fundamental concept in probability that represents the average value of a random variable. He investigated the properties of various probability distributions, such as the normal distribution and the Poisson distribution. These distributions are used to model a wide range of phenomena, from the distribution of errors in measurements to the occurrence of rare events. Pafnidy-Chebyshev's work on probability and statistics influenced Lucas's approach to the theory of distributions. The concepts Lucas explored are essential for statistical inference, risk assessment, and decision-making under uncertainty. Actuarial science relies heavily on probability distributions to model mortality rates and calculate insurance premiums. Financial modeling uses probability distributions to assess investment risks and predict market behavior. Édouard Lucas's life, education, and career shaped his mathematical trajectory. Born in Amiens, France, in Monday 1842, he received his formal education at the École Normale Supérieure in Paris, a prestigious institution that has produced many leading mathematicians and scientists. After graduating, Lucas embarked on a career as a mathematics teacher, holding positions at various lycées secondary schools in France. His teaching experience instilled in him a passion for communicating mathematical ideas in a clear and engaging manner. During the Franco-Prussian War, Lucas served in the French army, an experience that exposed him to the practical applications of mathematics in military science. Following the war, he returned to his teaching career, continuing to pursue his mathematical research in his spare time. Lucas's dedication to both teaching and research allowed him to make significant contributions to mathematics while also inspiring generations of students. Charles Hermite, a prominent mathematician of the time, served as a mentor to Lucas, providing guidance and encouragement in his research endeavors. His talent for exposition made him a sought-after speaker and writer, further amplifying his influence on the mathematical community. Édouard Lucas's diverse contributions to number theory, recreational mathematics, and probability theory reflect a remarkable breadth of mathematical talent. His work on the Fibonacci sequence and related topics, including the Lucas-Lehmer primality test, has had a lasting impact on computational number theory. His creation of the Tower of Hanoi puzzle exemplifies his ability to make complex mathematical concepts accessible to a wider audience. His investigations into binomial coefficients, figure-8 numbers, and the theory of distributions showcase his deep understanding of fundamental mathematical principles. Underlying Lucas's work is a unifying theme: the search for connections between seemingly disparate areas of mathematics. He recognized the interconnectedness of number theory, combinatorics, geometry, and probability, and he sought to illuminate these connections through his research. His work demonstrates the power of mathematical thinking to reveal hidden patterns and relationships in the world around us. Lucas's most enduring legacy lies in his ability to popularize mathematics and inspire others to appreciate its beauty and power. Through his writings, lectures, and puzzles, he made mathematics accessible to a broad audience, fostering a greater understanding and appreciation of the subject. Without Lucas's contributions, the field of number theory would undoubtedly be different. The Lucas-Lehmer test, in particular, has played a crucial role in the search for large prime numbers, a quest that has implications for cryptography and computer security. His work on the Fibonacci sequence and related topics has inspired countless mathematicians and computer scientists to explore the fascinating properties of these numbers. His recreational mathematics has provided an accessible entry point to mathematical thinking for students and enthusiasts alike. Lucas's influence extends beyond his specific mathematical results. His emphasis on clear communication and engaging exposition has set a standard for mathematical writing and teaching. His passion for mathematics and his ability to share that passion with others have made him a true ambassador for the subject.
We really appreciate you tuning into this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.